Question 3, we have nuclear fission and fusion. The graph shows the variation of the binding energy per nucleon for nuclides with a nucleon number greater than 40. So just make sure that you understand this idea. A nuclide are specific nucleuses, and a nucleon is either a proton or a neutron, something at a particle, the basic particle that resides in your nucleus. So we have defined binding energy. Now this basically is the total energy that is binding your protons and neutrons within a nucleus, or the amount of energy that you need to use to separate your protons and neutrons into their constituent parts. So for instance, say if I had the helium nucleus, so we got 2 and 4, and it'll be 2 plus, and we had to separate it out into a neutron, a proton, and a proton into its separate parts. The amount of energy to do this, the energy that I have to put in there to do that, is your binding energy. And obviously the greater the binding energy, the more difficult it is to separate their constituent parts. They are more stable. So then it says, on the graph, label with the letter S the position of the most stable nuclide. Well, that will be the one where you have got your highest binding energy. So it would be over there, probably at the very top there. S there, you have to use the S. And state why the nuclide you have labeled is the most stable. Well, it's got the highest binding energy. So it's got the highest binding energy. It's got the most energy that you'll need to put in to separate it into its separate parts. Now, going on to the next question. It says here, in a nuclear reactor, a nucleus of uranium-235 fissions into barium 141 and krypton 92. The equation for this fission is given by the following. So obviously you know that this, when it talks about here the uranium-235, this is giving the number of nucleons, number of protons, and the number of neutrons. And here it goes to barium and to krypton. So it says, use the graph to show that the fission of one nucleus of uranium-235 will release about 200 mega eV of energy. So what we're going to do here is we're going to look at the binding energy of the uranium and the binding energy of these two, and then the difference between on this side with this side will give us an idea of the amount of energy that has been released. So going back to the previous page, to my graph here, this graph. Now I have uranium-235, so that is going to be somewhere over here. This would be uranium-236, so we're about over there. That is about 7.6. So uranium-235 is got a binding energy of about 7.6. For your barium, which is 141, if I go 141 here, that's just about 140. We're around about over there. We're about 8.4 mega eV per nucleon. And your krypton, which is 92, if I go here, 92 would be 148. This would be 92. So going up here, we're over there. Going across, we're about 8.7. So we're going to need to remember these facts, as we're going to need them for, if I just go back over the page here. Alright, so here, if I take uranium-235, the total binding energy for uranium-235 is going to be 235 times the binding energy per nucleon, 7.6, and I multiply that out and I get 1786 mega eV. That's for the uranium-235. For your barium 141, you're going to get 141 times 8.4, and that gives you 1184.4 mega eV. And for your krypton, which is 92, that's going to be 92 times 8.7, we said was the binding energy per nucleon. That's going to be 800.4 mega eV. So these two are the products. So if we look at the total binding energy of the products, we have going to have 1984.8 mega eV. Now you can see here that your binding energy, your total binding energy for your product is greater than for the original material. So what's happening here is this has become more stable, and therefore you're going to need more energy. You're going to need this amount of energy to separate into its constituent parts than before. So the uranium was less stable, and therefore this amount of energy, when it went from there to there, it had to give out about 200. If you subtract this 1984 and you subtract from that, you subtract minus 1786, you get about 200 mega eV. That was actually released. That's released because this is at a more energy, a more stable energy state. So it's almost like you've got a situation where you have an energy well. So this may well be your uranium, your total with the uranium. You've got to get out this, you've got to give this amount of energy for it to separate. And with the barium and the krypton, you now are in a deeper energy well. So you've actually gone lower down. So you've given out more energy. So there is more energy to get out of that energy well. So it's going to be more stable. Looking at question 3, it says the mass defect in the reaction is 3.1 times 10 to the negative 28 kilograms. Calculate the number of uranium-235 nuclei that must fission in order to release 1 kilojoule of energy. So this is the mass defect. This is the difference in mass. So here this mass is actually being converted into energy by a formula E is equal to mc squared. So we put that in 3.1 times 10 to the negative 28 times c squared, 3 times 10 to the 8 squared. And we get there 2.79 times 10 to the negative 11 joules. That's the energy that is released for every fission, every reaction. But we want 1 kilojoule, so it's 1000 joules. So we divide by the amount of energy for one fission, 2.79 times 10 to the negative 11. That's joules per fission. And we get, out of that, we get 3.6 times 10 to the 13. We would need that many fissions, or that many reactions that would need to take place to give that amount of energy. Finally, it says, outline how this fission reaction can lead to a chain reaction. So we've got our uranium, and it's uranium, and we have fission. It divides into two parts, and it gives out two neutrons like that. Now if those two neutrons hit two further uranium, they may give out two further neutrons each. So now we've got 4 neutrons. And if each one of those hits further uranium, they would also give out 2 uranium. So you see here, 2 neutrons. So you see here how you're getting an increase in the number of neutrons and an increase in the number of fissions that are taking place. So it started with 1, now you get 2, then you get 4, and here you would have 8 occurring, and so you're getting this chain reaction, you're getting this rapid increase in the number of fissions. Each one of these are supplying energy, are supplying some energy, and that's getting added to the overall energy, which leads to the if it's a uncontrolled chain reaction, leads to a atomic bomb explosion. Finally, here we look at the idea of fusion. It says intensive scientific effort is devoted to developing nuclear fusion as a future energy source. Discuss what could be the social and environmental benefits of using nuclear fusion as compared with nuclear fission. Well, nuclear fusion, you don't have the harmful waste products. So you're not getting those that you have to worry about for thousands of years, making sure they don't come in contact with humans and plant life and so forth. Hydrogen is abundant, so you've got lots of it available. You don't have to mine for it, so you don't need to mine for uranium and so forth. You don't need to mine for it, such as with uranium. Also, we have it that it doesn't produce the same sort of harmful radiation. The harmful radiation as does nuclear fission. Okay, so there's three marks there. You need to have 3 separate points. One further point is that nuclear fusion, with nuclear fusion, we have a higher energy density. Higher energy density. So per unit mass, it's giving out more energy.